In the first lecture, I introduced the path integral, derived its formula starting from basic quantum mechanics. In the second lecture, we considered a symmetric well in which a particle is confined and then started evaluating the path integral. Today, that process will be completed. We'll do the fluctuations part of the path integral. Then we shall apply it again to the double well and have a very definite physical result at the end, which is the splitting between the two lowest levels of the symmetric well. So let's start. Right, so that's where we are and that's where we're going. This is a very quick recapitulation. Here is a symmetric potential, the equation of motion which follows from the Lagrangian. Here is the total energy, and notice over here that the energy is the kinetic energy in imaginary time. So this comes with a negative sign to it, and this quantity over here does not change with time, it is conserved. So that's just a quick reminder. And this is to tell you where we are going. If you had an ideal computer which could solve the Schrodinger equation for this potential to any accuracy, you would find that there are two states, n equals 1, n equals 2, which are extremely close to each other. And to separate them is not possible in perturbation theory, but it will be possible to actually use our process and to use the path integral method, and we shall indeed do that. Okay, so here is where we are. The total amplitude to go from A to B, and remember, we start at time minus t over 2, and we end at time plus t over 2. The amplitude gets split into two parts, that is the 0th level, that is the classical amplitude, times the fluctuation part. The fluctuation part is what we're going to calculate today. I remind you that these xi's over here are the fluctuations away from the classical path, as you can see over here. So A to B is the classical path, and then the fluctuations are this. Okay, so in lecture number 2, the previous lecture, we expanded xi in a complete orthonormal basis, and these were the eigenfunctions of this operator, this minus d2 by d tau squared plus the second derivative of the potential evaluated on the classical path. You see, v is a function of x, but we're not going to take all x. We're not going to take x's over here or over here. We're going to take x's only along this classical path. And this is the second derivative of that. Now, this is an operator which will have eigenfunctions. We're going to call those eigenfunctions phi n. So that operator acts on phi n, gives us the eigenvalue back, that eigenfunction. And the boundary conditions are just what I told you, that at minus t over 2, and remember that t is going to be a very large number. So phi n at minus t over 2 and phi n at plus t over 2 are both 0. So now you stick for psi over here, the complete basis set phi n, and this is what you get. Now, we were to do an integral over all x's but we wrote x as x classical plus I. And so this measure over here then is converted into an integration of the coefficients, Cn. We then simply did the Gaussian integral, and we got this. So this is a recapitulation of what we did the last time. We have a sum over all the eigenvalues, lambda n, going from 0 up till infinity. And it's fine. It looks very good, but there is a problem. And that problem is that what if this lambda n is ever 0? Then we will be dividing by 0, and that means there's serious trouble. It means that this infinite product, which of course is the same as the determinant of this operator S double prime. S double prime is just this operator here. So this is an operator which has got a lot of eigenfunctions and eigenvalues, but the problem is that what if one of these is 0? And this is called the zero mode problem, and this is what makes the whole instanton thing a little complicated, but we learn how to deal with that. Okay. This being a delicate matter, we shall do it stepwise. In the first step, I point out that there is time translational invariance here. So imagine that I was to put tau minus tau prime over here, tau minus tau prime over here, and tau minus tau prime over here. But here it doesn't matter at all because d tau remains unchanged. It becomes d tau prime. And that means that I can shift I can shift this classical solution backwards or forwards in time, and that will still be a solution of the equations of motion. So in other words, what we have is this being just as good a solution as with tau prime equal to 0. All right, that's what we call time translational invariance, and it follows because of the equations of motion. Now, we come to the second step. Now, this operator, I claim, has an eigenfunction with 0 eigenvalue, and I claim that that eigenfunction is this, which means that if I operate this thing on xc dot, then I should get 0. So 0 times itself is 0. And now let's check to see if that's true. Right? So I'm going to operate on xc dot, which is the same as dxc by d tau. Now, d by d tau commutes with d2 by d tau squared, so I can take this out. And you see, I have taken that out. And this d by d tau acting on this, let's figure out what that is. So d by d tau acting on this, first of all, will give you a second derivative of v with respect to x. And then you have to differentiate what's inside by tau. And so that means that what I have is this is equal to this. But then you recognize what's over here. This is just the equation of motion. And so, this being 0, we have proved that dxc by d tau is indeed a mode. That is to say, it's an eigenfunction, and it has got 0 eigenvalue. Okay. And I should also point out that xc dot obeys the correct boundary conditions. So if you look at it at minus t over 2, well, that was our, so you can think of this as the ball rolling down the hill, starting at 0 speed, and then going to the other side of the hill and arriving there with 0 speed. So the boundary conditions are obeyed.
Professor, a slight notational confusion over there with step 2. Since we're defining the operator S double prime on the left of that, but we already have the classical path fed into the potential, shouldn't it just be the potential as a plain operator there instead of a potential with the classical path substituted?
No. This is, we have expanded around the classical path only. You cannot let this over here be arbitrary. This, after we did the functional expansion, we said that we're going to consider fluctuations around the classical path. We're not going to fool around with the classical path itself. And so I'm sorry, but we have to put xc over here. Well, the zero mode function is x dot, xc dot, but it has to be normalized. We can do that. That's easy enough because it doesn't vanish anywhere. And you see that from here, we can easily get, we can just square this side, integrate it, and then divide by c, and that'll give us the proper normalization. And let's also notice that this over here, xc dot squared, by the fact that energy is conserved, that's equal to square root of 2v on the classical path xc. Okay, and this is just the action for a single instanton, 1 over square root of that, actually. So now we have to start worrying about why we got that 0 and how to fix that problem. Let's go back to the source. So we are looking at fluctuations. In other words, we are integrating over all possible trajectories x. And since xc has been fixed, that means we're integrating over the xi's. But integrating over the xi's means that we're actually integrating over all the cn's. And don't worry about this square root of 2 pi h bar, because that's just a convenient normalization, which we can easily slip into this normalization n. And we'll be able to figure out what this n is with or without this. Anyway, this is just convenience over here. But here is where we are doing the Gaussian integral. And the Gaussian integral is that of the eigenvalue, Cn squared, and we're integrating over all possible values of Cn. Each one of those Cn's has to be integrated from minus infinity to plus infinity. And that's, of course, how we got over here. Here I've not told you anything new. It's the problem only with lambda 0 equal to 0. And you see that if lambda 0 over here is 0, then there's no damping over here. There's nothing that will cause this exponential to go down at the edges, at minus infinity or plus infinity. And so this integral is infinity. So we have now to be a little clever. We understand where this is actually coming from. That infinity is coming from the fact that it takes no effort to slide an instanton along this path. In other words, the instanton could cross the axis. So think of x versus tau Where is the origin of that? It could be here, 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 anywhere along this path, and there are infinite number of positions over there. So the fact that there is a symmetry, time translational in symmetry, has given us a headache. It's given us an infinity to deal with. Now, the last time what I did it wrongly, deliberately wrongly, was I said, all right, I'll just do an integration over t, and so just multiply this thing by capital T. So t over 2 minus t over minus t over 2 is t, and as t goes to infinity, that goes to infinity. Now we will be a little more careful. So remember, earlier we had expanded around the classical path like this. Classical path plus fluctuations. Now I am going to be a little more careful and say, hey, why don't I choose a slightly different way of doing the functional integration? And I do an integration over x, but with the argument shifted slightly. So make it tau minus tau prime instead of taking tau prime over here equal to 0. In other words, I'm still integrating over all paths, but I've chosen my path a little differently. Okay, so that means we have this relationship with which we can now manipulate. What I'm going to do is multiply this side and this side by the zero mode, phi 0 of tau, and integrate all the way from minus t over 2 to plus t over 2. Okay, that's exactly what I've done over here. Let's see what happens when I put in phi 0 over here and then integrate over tau. Well, the phi's are orthogonal to each other, orthonormal rather, and so the only thing that remains over here is C0, and that's the C0 that comes over here. So that fixes one thing. Then I'm going to multiply, then I have, of course, the second term, which is phi 0. That's the thing I'm multiplying with, xc of tau. That's this over here. And remember that phi 0 is xc dot. We saw that that is we saw that that is the zero mode. Okay? So when normalized properly, you remember we had to put a normalization constant c. We even have an explicit form for that. But let's put in phi 0 equal to c x dot. Good. Now look at this thing. Phi 0 xc. That's xc dot xc. What is that? That's just half d by d tau of xc dot of xc squared. Differentiate this. The 2 cancels. There's xc dot xc. Fine. But then this by the fundamental theorem of calculus says, the fundamental theorem of calculus says evaluate xc squared at the top minus xc squared at the bottom, and of course both of them are equal, and so this is equal to 0. Those are our boundary conditions. Remember that xc at minus t over 2 is equal to minus a, and xc at t over 2 is equal to plus a, but when you square them, they're the same thing. Okay, so now we have this equation with this term having gone away. And so C0 of tau prime, you see, there's a dependence now on tau prime. That dependence we will get to, that dependence we will use to get our measure. So C0 of tau prime is equal to this over here. Let me now differentiate this with respect to tau prime. In other words, see, I had chosen the path x of tau minus tau prime. And now I want to see what happens when I slightly shift tau prime. That means I take the derivative. I take the derivative, well, over here, there's only one thing that depends on tau prime, and that is this. So I have to differentiate with respect to tau prime, x of tau minus tau prime. But look, this depends on tau minus tau prime, which means that I can make this d by d tau prime d by d tau with a minus sign. And that minus sign comes out over here. So I have this integral before you. And now I will look at what's over here and just stick this here. That will immediately tell us some things. So the first term is xc dot. So dc0 by d tau prime becomes this integral over here. But this other thing over here will integrate to 0, because what we've done is, so this is basically phi 0 of tau, and that's going to be orthogonal to all of the others. One just has to do an integration by parts. Again, our boundary conditions will kill all of those terms, every single one of those terms, giving us 0 over here. And now this thing, we know what it is. This is S1, and this C has, when we stick that C1 as square root of 1 over S1, then we get dc0 by d tau as this, and now we're done. So finally, we know how to replace the integration over C0 of time, C0 of tau, tau is imaginary time, with the integration over all instanton times going from here to here. So this is our final result. What I did wrong the last time, and let me say this, I did it because to go through this reasoning would have been a little confusing at that time. But I went through this and I simply said, oh, dc0 is equal to d tau. In doing so, I missed out this crucial factor, square root of S1 over 2 pi h bar. But we shouldn't be ashamed of such things, as long as they clarify things. However, now we are in good shape. So let's correct our earlier mistakes. The amplitude for a single instanton, so n equals 1 means one instanton only between minus t over 2 and plus t over 2. Here is the classical part, S0. Just take that out. And actually, just a point of notation. This is, I meant over here 0th order, which means classical. And here the lowest order classical solution has been put, which is 1 instanton, S1. And then this part, you just saw, that's from the 0 mode. This t came from integrating over time, from minus t over 2 to plus t over 2. And now you see, I have excluded the 0 mode, because the 0 mode is in here. I don't need, in fact, it would be wrong to put n equal to 0 from here. It has to be n equal to 1. And so what we have is the determinant, but with the 0 mode excluded. So this prime over here means that the 0 mode is not to be included. It's only n equals 1 up till infinity. Fine. So then let's define a quantity. Because I'm going to define it because it'll come up again and again. So this square root of S1 over 2 pi h bar, and there's this determinant of S double prime, which is this thing. And note that I always have XC over here. Here, I want a ratio. This is just a definition, okay? But what I've done is basically use the harmonic oscillator over here. The ratio of this to this will be something that we'll be able to compute more efficiently. So this is a definition. In which case, we have to correct for the fact that this has been put in the definition by dividing this out. So this is the same as that. There's the normalization constant and all this. The important thing to notice is that this exponential has come here as well. And this is the exponential with a single instanton in it, S1. Okay. Now, in lecture number 2, I'd actually calculated this and found that this was what you see over here, omega over 2 pi h bar hyperbolic sine omega t. And anyone can take the limit of this as t becomes large. You know that hyperbolic sine is e to the omega t minus e to the minus omega t, the whole thing divided by 2. So that 2 is cancelled by this 2. As t goes to infinity, only the positive exponential here contributes, which means that when it goes upstairs over here, and when you take the square root, then you get e to the minus omega t by 2. And then the rest you can see is just omega over pi h bar. And that's our grand result for a single instanton, n equal to 1. There's this normalization factor, and each instanton will contribute this much, and this second part is going to exponentiate when I have not one instanton, but 3, 5, 7, 9, 11, etc. instantons. These are instantons which will take you from minus a to plus a. Not the ones that will bring you back to minus a. Those will involve even numbers of instantons. By the way, I am not distinguishing between instantons and anti-instantons. Both carry the same action, and saying anti all the time takes a lot of time. Okay, so once again, to remind you from lecture number 2, suppose you have 3 instantons. You start from minus a, you go to plus a, after a while you come back to minus a, and then you go to plus a again. So 3 times you've crossed the axis. 1, 2, 3. 3 instantons. And the second instanton has to come after the first, the third has to come after the second, hence this order of integration. And as we discussed last time, you can generalize this to any n, which means that this, when you sum over all odd values of n, 1, 3, 5, 7, etc., then this is just the expansion of hyperbolic sine. And so you get sine of exponential of a single instanton. Now, again, I remind you that it's the single instanton which we are able to compute. There are no two instanton or any other instanton solutions which are known to mankind, or at least to this man, or to a lot of, they're simply not known. So it's a single instanton, and there can be any number of them. But the classical equations of motion may or may not have multi-instanton solutions. They're simply not known. Okay, so here is the result, our main results obtained so far. The amplitude to go from here to here is this. The amplitude to stay where you are, in other words, to go from minus A back to minus A, is got by summing over all n values which are even, 0, 2, 4, 6, etc. And so that gives us a cosh. And again, this is merely reiterating what I said earlier, that the single instanton action is this. And now the hard part of the calculation begins. So what is the ratio of this infinite determinant to this infinite determinant? The difference between this and this is that the zero mode has been extracted from this. Well, I'm going to come back to the calculation of this ratio over here. But before this, I have to tell you why it is, what physical result we are going to achieve by the end of this lecture. Okay, so we have expressions to go from here to here, as I said, or to go from here to here and come back, amplitudes for that. But if we want to calculate energies or differences in energies, then we have to understand that all energy eigenstates have to have definite parity. So the Hamiltonian commutes with the parity operator in this case, and so the energy eigenstates will be either positive or negative parity. Let's look at the zeroth eigenfunction, h0 equals E0 times 0. And the first one after that, so n equals 1, will be this. The lowest energy state has to have even parity. So this state projected onto the bra A is the same as the same state projected onto minus A. Why is the ground state symmetric? Or rather, why does it have even parity? Because we know from our experience with the Schrodinger equation that if there is a node, then that node means that there is curvature. Curvature always means more kinetic energy, and so a symmetric wave function will always have lower energy than an antisymmetric one. Similarly here we have an antisymmetric wave function, one projected onto A and one projected onto minus A, differ with a minus sign. Okay, so now let's calculate the amplitude to go from minus A to plus A. Here is the Hamiltonian, which causes the transition. And remember that we've gone to imaginary time. So this was e to the I h t over h bar. And then we made t go to I tau. And so we got minus over here. Here, let me stick in the unit operator. The unit operator is just a sum over the eigenstates n. And now you see h acts on this and gives you the energy of this state, which then comes out, and then this is no longer an operator, you can take it outside. And this will give you the wave function. This will be phi n star of minus a. Okay, writing this out like this. So now, of course, this over here is a sum over all n, but as you go up, the energies are getting bigger. And now what I'm going to do is let t become larger and larger, which means that this will be the dominant term. This will be the next dominant. And then all the others over here are going to be negligible. And if you look at, of course, we can do it all very systematically, but I'm now just going to look at the difference in energies between E0 and E1, just these two states themselves. Okay, so now what we have is from here that we have this thing being A0 squared and this thing being this over here, magnitude squared. But this and this are normalized to the same values, which means that I can write ZLR as this thing. Similarly, going from left to left, see this left to right was going from here to here, but we can go from here to here and come back. And then I go from minus a back to minus a. The same operator, evolution operator, is stuck in over here. The difference is that instead of minus, I get plus. So now that gives me an idea. What if I take the difference between this and this? Well, that gives me the exponential of E1 minus E naught t over h bar. And I repeat that this is for t large. So all this other junk over here has gone away. So now we have our grand formula that the difference between these two tiny energies, E1 and E0, you saw at the beginning that I had drawn the level structure and said that there are two energies that are very, very close to each other. And now, if we have explicit expressions for ZLL and ZLR, just stick them over here. And then take t going to infinity, and we will have this. So, just to make life a little easier, we'll put omega equal to this thing, single instanton action divided by h bar, and k as before, and then we have cosh minus shine and cosh plus shine. Well, take their difference. This minus this is, see, the positive exponentials here cancel out. Here they add up. So I get e to the minus omega t over e to the plus omega t. This goes on top. Now you take the limit. Okay, well, log of e to the minus 2 omega t is 2 omega t. You divide by t, so miraculously, the times have cancelled out. I can now make t go to infinity, no problem. And so I get this result. Delta E is equal to this in terms of k, and k is, well, we're going to come back to that. So here is our grand result. If there was no tunneling of the particle from the left well to the right well, the energy of a particle in the left well would be half h bar omega. In the right, it would be the same. When there is tunneling, the symmetric state comes down by this amount. The antisymmetric state goes up and becomes this amount. The splitting between them is this. So you see, we have made an enormous amount of progress. The only thing is, what is the value of K? And now this is going to be the hard part of the calculation, and I will not complete it. But I will tell you the answer. Okay. So, by the way, this is done in the textbook in Manu Paranjape, and it is also in the references, other references that I've given you, including a new reference. But that's only if you want to go into the evaluation of K and you feel compelled that you should know it. But I'll give you hints with which you can understand the argumentation in there. Okay, so suppose that there is an operator like this whose infinite determinant you want to calculate, with the boundary conditions that phi at minus t over 2 is 0 and phi at plus t over 2 is 0. In terms of diagrams, here's some arbitrary symmetric potential W of t. So this could be anything. It could be a harmonic oscillator. It could be the potential x squared minus a squared whole squared. It could be anything. It could be something even more complicated than that. The eigenfunction has to be 0 here and here. That's our condition. Okay, now as lambda over here becomes bigger and bigger, it really doesn't matter what W is. So in the limit that lambda becomes very, very large, W becomes irrelevant, which means that this thing over here, minus d2 d tau squared phi equals lambda phi, is the relevant equation to solve. In other words, you have a particle in a box situation. You have just signs of different frequencies. These satisfy the boundary condition here and here. So if you have two potentials, W1 and W2, the eigenvalues of the two potentials will approach each other in the limit of high number of n's. That is, when lambda is large. Okay? I think that's fairly clear, because when you're very, very high up, you don't care about, then the eigenfunctions don't care about what potential is below. Next, we define this infinite product from 1 up till infinity. So lambda is some number over here. I'm not saying it's large or small, some number. So lambda 1 minus lambda, lambda 2 minus lambda, and these are the various n's. We have no guarantee that it will converge, but if lambda n1 and lambda n2 become close to each other as n goes to infinity, then it is very likely that they will converge. And then you can always test for convergence. Okay. Now, in the limit where lambda goes to 0, so this is 0, this is 0, and you just get the limit of determinant of one over determinant of the other. On the other hand, when lambda goes to infinity, then, well, the numerator and the denominator become the same. So these are interesting limits of f of lambda. Okay, now, given any potential, and for any lambda, let me go back and say that lambda over here is is of course, it'll be fixed by these boundary values, but this is the eigenvalue problem. The Cauchy problem is different from this. The Cauchy problem is that you want to solve this with some initial conditions. Not boundary conditions, but initial conditions. So the ball starts off, let's say, at position 0 with initial speed this equal to 1 or 2 or whatever. This means derivative, actually. I should have a dot over here. But that's clear here. So you start from here, and the ball starts rolling. You can always solve this problem. It's a deterministic problem. Okay, in general, if you start with some speed, this ball will roll. Maybe it'll come here, and then it'll roll back to where it was. It can go nearly up till A, or it can go beyond A. Only when it stops at A will you have an eigenvalue. That's when only when lambda is equal to lambda n will you have an eigenvalue. Otherwise, it'll overshoot or undershoot. Okay. Next point. Every potential will give the same value for phi lambda of t over 2 for large enough lambda. So if lambda is very large, then what is below doesn't matter. We just talked about that. So you could put W1 equal to 1, or you could put it equal to omega squared. It's, again, a simple reiteration of what I said earlier. Now, if you look at this thing, which I just discussed, and you look at this thing, which is the value of the function phi lambda on the other side at t over 2. Now, you see that when lambda is equal to lambda n, then it will have reached the top over here. And similarly over here. So the poles and the zeros of f of lambda and g of lambda are exactly at the same values of lambda. Now, there's a theorem of complex variables that if you have two functions that have the same poles and the same zeros, then they have the same function. Furthermore, they also agree for large lambda, and hence they agree everywhere. So these f and g are what are called holomorphic functions. And then Liouville's theorem, which says a holomorphic function which is a constant at infinity can be nothing but a constant. So then you have these powerful theorems from complex variable analysis, which then tell you that f and g are the same functions, exactly the same. Okay, now these are things that we have learned, and in the textbook, this has, I think, not been explained in the simple terms that I've given you, but it's all there in that textbook. One last thing I need to remind you from the theory of differential equations. If you have any second order differential equation like this one, so this thing equal to 0, this has to have two linearly independent solutions. For the zero mode, you see, this is a zero mode equation. This is 0 times phi. Now, we just found one of them, which was this x dot. We showed it explicitly. You take, you stick this in here, and this satisfies it. But what's the other one? So then you go back to the theory of differential equations. If you have f and g, which are two independent solutions of a second order ordinary differential equation, then the Wronskian, which is one function times the derivative of the other minus the derivative of the first times the second function, that is a constant and it has to be non-zero. Okay? That means we can take a linear combination of f and g, we can satisfy the differential equation itself over here, but we can also satisfy the boundary conditions. And that's all that those are all the principles that are involved. After that, it's a little bit of calculation, and it will take you 2 or 3 hours, maybe less, depending on where you're coming from, to find that K is actually extremely simple. This ratio of infinite determinants is omega to the 3/2. What is omega? Omega is the second derivative of the potential at either plus A or minus A. Remember, it's a symmetric potential, and so its second derivative will be symmetric as well. And so this omega is known, of course, that's h bar. And what is this A? Well, this A is exponential of this thing. So you start from the point minus A and you go to plus A. That's the A over here. You integrate from here to here times this thing. Now, this is not very, this is something that comes because of the singular nature of the integrands. Look over here. When x approaches A, you have a logarithmic singularity. What about over here? V of x, let's say you take the potential x squared minus a squared squared. When you take the square root of that, you get x squared minus a squared. Okay, then you integrate that. Well, there's a logarithmic singularity there. So that logarithm and that singularity from here and the singularity from here will cancel each other, and you'll get a finite result. My final slide will be this. So suppose your V of x was this model potential, x squared minus a squared squared. Then here are the two states, positive parity, negative parity, and well, omega squared, of course, is, you just take the second derivative of this, that is omega squared. S1, which is either x dot squared or equivalently square root of 2vx, well, just stick this in here. It's a simple integral. You get 2/3 a squared omega. Here, as I said, there's a logarithmic here, logarithmic singularity here, logarithmic here. And okay, here there is no order of square root of h. But remember that our calculation is accurate only to quadratic order. We can't go to cubic, which means that we're not sensitive to square root of h bar corrections. Finally, put this into the formula for delta E that you saw on the previous slide. And here is our final answer. And just out of dimensional reasoning, I've put m back over here and m back over here. And this is the grand answer that we have been looking for. So what's the important thing over here? This exponential, which has got h bar at the bottom. This is a result that you would never be able to get from perturbation theory. It is purely non-perturbative. It is leading order non-perturbative. This stuff over here, one should not trust too much, because there is, see, this, you have a square root of h bar over here. And I said we were not able to go to cubic terms. So take this over here with a grain of salt, but what's important is this thing. This exponential is what dominates this formula over here. And this will become more and more accurate as h bar goes to 0, which means that this term dominates this. I mean, imagine you were to take the logarithm of delta E, then you'd have the logarithm of this, and then you'd have the logarithm of this, which would be something of order 1 over h bar. Okay, so I should say that you can include corrections of square root of h bar, but then that requires combining this path integral method with a kind of perturbation method as well. But the base of that would be a calculation like the one that you've just seen. So that's all for today. And the next time we shall get into tunneling.